So last class we have seen the definition of electric line of force. Now in the definition we have seen two or three examples of lines of force. There are the lines of force near a positive charge, next near a negative charge, next near a pair of equal and opposite charges. Three cases we have seen. So based on the definition of lines of force and how the lines of force are present in electric field in the three examples, many properties of electric lines of force are actually obtained. So this is properties are very useful. So it's actually from the board examination point of view, they carry about these properties carries about 2 to 3 marks, roughly mostly around 2 marks. So any three properties can be written. So any three. So properties can be written. Now the very simple property. So just look at the diagram of the electric lines of force in three different examples which you already seen. I'll just go back to the page. So this was the page. Just look at this diagram. So this is a simple case, example 1. It's an isolated positive charge. Near an isolated positive charge, it can be seen that the electric lines of force are directed away from the positive charge. That means they are diverging. They are said to be diverging. That means we start at this positive charge. These two lines of force are separated by a certain distance. But as we move away from the positive charge, you can see that the lines of force are moving away. They are said to be diverging. So the lines of force near a positive charge are diverging away from the positive charge. But what about the negative charge? Can we see that the lines of force are actually converging at the negative charge. So if we start at a point far away, say somewhere in this region, these two lines of force, you see, they are far apart. But as we go towards the negative charge, you can see that the lines of force are approaching closer and closer. So they are said to be converging at the negative charge. So always near a positive charge, the electric lines of force will be diverging, and near a negative charge, the electric lines of force will be converging. Then what about the pair of charges? This is also the same thing. In this case also the same thing can be seen. Away from the positive charge, near the positive charge, the lines of force are again diverging, and near this negative charge, the lines of force are always converging. So this is a general rule. Always near a positive charge, they will be diverging, and at a negative charge, the lines of force will be converging. So these are two simple, very simple properties of the lines of force. Now similar to these properties, these two very simple properties, even other properties can be obtained. Now consider a region very close to the positive charge. Now previously we have seen that supposing this positive charge, just see here, imagine that this is a positive charge here. Near the positive charge at any point, the electric field vector or the electric field intensity at this point at distance r, it is inversely proportional to the square of the distance. This we have seen previously. So just see the equation, electric field near charge q, it is inversely proportional to the square of the distance from this equation. That means if we consider large distance from this charge q, the electric field, if large distance is considered, r is more, electric field is less. That means electric field vector, or this is also called as electric field intensity or the electric field strength also. So electric field strength is less at more distance, but at less distance from the charge q. So when distance r is small, the electric field strength E will be more. So this is a very simple relation. Now just observe this here. Now consider this particular region, say this way, this particular area, a small area we are considering. In this area it can be seen that close to the, we are considering this area very close to the positive charge. So two lines of force are actually passing through this particular area. Now consider the same area at a more distance. Same area I am considering at a more distance. You can see that only one line of force is passing. So close to the positive charge where the field is strong, that means strength of the electric field E is high. Lines of force, more lines of force are passing through a given area. That simply means that lines of force are closer. This is because why more lines of force are passing here in this area, because the lines of force are actually closer, but they are diverging away from the positive charge. So if we consider the same area at a more distance, you can see that only few lines of force. Here in this diagram only one line of force is passing. The reason for this is lines of force are well separated. they are more separated at more distances. That means where the field is less strong. That means the strength of the field is less, lines of force will be well separated. So this is another very important property. Wherever the electric field is strong, that means E vector is more. There the lines of force are closely spaced, and wherever the E vector is less, where the electric field is less strong, that means strength of the electric field is less, the lines of force are well separated. This is a very important property of these are actually this is a very important property of practically very useful property of the electric lines of force. Just by looking at the lines of force, we can say where the electric field is strong. Wherever the lines of force are closely spaced, it means that field is stronger there. Wherever the lines of force are far apart, well separated, the electric field is weak there. So this is very useful property. Just the magnitude of electric field vector or the magnitude of the strength of the electric field E can be roughly known from the spacing between the lines of force. If the spacing is less, they are closely spaced, field is strong. If the spacing is more between the lines of force, they are well separated, the field is weak, or the strength of the electric field is less. That way the magnitude of the electric field strength can be roughly known from the spacing between the lines of force. So this is another very important property. Now similarly, even other properties, just see here, I am not putting the numbers, just we'll go back to the page again. So we got many properties. The lines of force are diverging. Next we got the lines of force are converging near a negative charge. Next we are getting some idea about the strength of the electric field by looking at the lines of force. Wherever they are closely spaced, there the field is strong. Wherever they are well separated, the field is weak. So this is another very important. Not just the magnitude of the electric field vector, even the direction of the electric field vector also roughly can be known from the lines of force. How? That also can be seen here from the very simple definition of the electric lines of force. Now just see here. Now we just consider the I'm again considering this particular say line of force here. So this is the line of force I'm taking. Now if you're what is the definition of line of force? When a free positive charge is placed, a tiny free positive charge is placed at any point, say here, whatever path it takes, whatever line or curve along which it travels, that line itself is called as electric line of force. So when we are putting a free positive charge here in this electric field created by already a bigger positive charge here is there, which is creating this electric field. Now in this electric field to the positive charge, we are putting a tiny positive charge. Then this is positive charge, this is also tiny positive charge. Here I'm just putting a spot here, observe the cursor, a tiny positive test charge I am putting here. So this positive charge is repelling that. So it's just pushed away. So if you consider the line joining this charge and this charge, that is the center of this test charge and the center of this big charge which is producing the field. Along this line the force will be present. Repulsion force is present. So that is repulsion means it is directed away from this charge, main charge. So it's exactly along this line. So in that direction only it will be pushed. So in the path taken will be in this direction only, this way. That's how we are getting the line of force, electric line of force. But how it is pushed in this direction? Because of the repulsive force, because repulsive force is acting in this direction. So in whatever direction force acts on a positive charge in an electric field, in this direction the force is acting. In this direction only electric field vector is present. That's what we have seen. So the force acting on a unit positive charge is this force here. You just observe this diagram again. Observe the cursor. So in this at this point A in the electric field near this charge Q, we're putting unit positive charge. Force acting on the unit positive charge, repulsive force. That force itself is electric field. So always any positive charge is placed at a point in whatever direction the force acts on the positive charge, that itself gives the direction of the electric field. But in that direction only line of force actually is formed because of the positive charge is moving along that line of force. So whatever is the direction of the line of force, that itself is giving the direction of the electric field vector there. And this direction of the electric field vector is taken as the direction of the electric field itself. So what is the direction of the electric field at any point? In electric field, it is exactly along the direction of the line of force. So here also, you put a unit positive charge here. So it will be attracted by this negative charge, which is producing the electric field here. So it moves down. So in this direction, force acts. So force acting on a positive charge direction will give the direction of the electric field vector. That means direction of the electric field. In that direction, only line of force is present. So always the direction of the lines of force give the direction of the electric field at any point, provided the line of force is a straight line of force. The line of force is a straight line of force. And what about a curved line of force here? We are taking a curved line of force in this direction, say at this point. Then at this point now, we are putting a unit positive charge or a free positive charge here. Then because of the repulsion of the positive charge, it starts moving away from the positive charge, but at the same time it's attracted by the negative charge. So instead of going directly away, so it it turns, and it goes along a curved path finally towards the negative charge. So this way the line of force, we have seen that it's a curved line of force. But now the important thing is at this particular point, in what direction the force is acting on the free positive charge. That direction of the force is nothing but direction of velocity. But what is the direction of velocity on a curved path? It is tangential. It is tangential. So along this tangential direction, the force acts. Because direction of motion or direction of velocity along a curved path at any point on a curved path is tangential. That's what we have seen in mechanics, especially in kinematics, direction of velocity. We got the direction of velocity from the definition of velocity. We got the direction of velocity to be exactly tangential to the curved path. So in that direction only really force is acting on the positive test charge. So direction of force is tangential. So that itself is the direction of force. Direction of force on a positive charge is nothing but direction of electric field. So direction of electric field for a curved path is nothing but tangential to the curved line of force. Curved path means curved line of force. So this is another simple case where the direction of the lines of force is helping us to get the direction of the electric field. If it is a straight line of force, direction of the line of force itself gives the direction of the electric field vector, or simply direction of the electric field. If it is a curved line of force, at any point on the curved line of force, electric field vector or electric field is tangential to the curved line of force. This way lines of force in any situation are helping us to get the direction of the electric field exactly. So this is another very important property. So thus we got another new property. Just look at this. So we got another new property. So not just the magnitude of electric field can be known, even the direction of the electric field also can be known from the lines of force. So whatever things we are seeing here are simple, nowhere any complication is there. Now consider another simple situation. Now consider a uniform electric field in a particular region. Supposing this is the region. In this particular region, for example, it is in the form of a rectangular box or a rectangular volume. So uniform electric field is nothing but an electric field in which, from the name itself it's clear, every point the electric field strength, electric field is said to be uniform. So what is the meaning of when is the electric field said to be uniform? An electric field is said to be uniform if the electric field vector or the strength of the electric field is same at all points, exactly same at all points in magnitude and also direction. For example, the electric field vector at this point is E towards right. Then every point it is exactly E towards right. Here, everywhere it should be exactly same both in magnitude and direction. Such a field is called as a uniform electric field. Later, what are the examples of uniform electric field? Later they will be coming more clearly in other topics of this same lesson. So in such a uniform electric field, how will be the lines of force? Now everywhere direction of the electric field is same. Everywhere the direction of the electric field is same. For example, at this point direction of electric field is rightwards. Here again it will be rightwards. Here again it will be rightwards. This way. This is possible only when the electric line of force, say passing through this point, is an exact straight line. So here it can be clearly seen that the electric line of force should be an exact straight line. Then only the electric line, direction of the electric field everywhere will be towards right only, exactly. Supposing it's curved means, just see the previous example again. If it's curved means what is happening? Direction of the electric field is tangential to a curved line of force. Here it is upwards. But at this point, electric line of force is going down. So electric field vector will be downwards. So this is not uniform electric field. So this can't be uniform electric field. So line of force has to be an exact straight line. So then only it can be a uniform electric field. Now another thing is, just see here, even here definitely electric lines of force should be straight in a uniform electric field. But is this a uniform electric field? Here the electric lines of force are straight. Now here though they are straight, it's not uniform electric field. The reason is closer to the charge where the electric lines of force are closely spaced. Electric field is stronger. So E vector is more, but far away E vector is less. So this is also not a uniform electric field in spite of straight lines of force. So how should be the lines of force? Uniform electric field means here the spacing is less, where the field is stronger, electric field is more, electric field vector is higher, or the strength of the electric field vector is greater. And here the spacing between the lines of force is less. That should not happen. Electric field vector here should be same. Uniform electric field. That means the spacing should be same. The spacing, the separation between the electric lines of force should be same, uniform everywhere. Then only that means that the strength of the electric field is same at all points. So not just the direction of the electric field is same at all points, even the strength of the electric field also should be same. So just see here the same example which you have seen. So here this is a uniform electric field. So I'll just so the best way to remember I draw a uniform electric field is now just remove the border of the rectangular volume so that only lines of force will be visible. So the line of force here is towards the right, not only through this point, even here also the line of force should be straight towards the right. Here also straight towards the right, here also straight towards the right, here also straight towards the right. Now another very important thing is though, so there should be lines of force. Clearly it can be seen that because directions are same from west to east here. Everywhere it should be west to east. And this is called as west direction, this is called as east direction. Notice this top direction, north, bottom direction is south. So west to east, west to east, west. Everywhere it's west to east. That means exactly the lines of force should be parallel straight lines. Then only the direction of electric field vector is same at all points, or direction of electric field is same at all points. That only it's a first condition for uniform electric field. Direction of electric field vector should be same, but not just direction, magnitude also should be same. But how can magnitude here and here same? Then that's possible. If it's more here, the spacing will be more. Spacing will be actually closer. That means separation between the lines of force will be less if the field is stronger. If the field here is weaker, the separation will be more. That should not happen. Spacing, electric field strength everywhere should be here. This region should be same. Means the spacing should be same. That means all the lines of force should be equally spaced. So here, whatever lines of force I have drawn, roughly they are equally spaced. They're very difficult to draw exactly equally spaced because it has to be measured with a scale. So roughly, I have drawn them to be uniformly spaced. So more accurately, it can be drawn carefully. Little more time it will take. But this is how roughly a uniform electric field is shown. The electric lines of force are parallel straight lines which are equally spaced. So that represents a uniform electric field. So what are the examples of non-uniform electric field? Example of uniform electric field, only one or two examples are possible in nature. But many examples are there for non-uniform electric field. Whatever examples we have seen till now, just see this diagram once again. So this is a non-uniform electric field because here lines of force are closely spaced, here they are far apart. And here the lines of force are curved, so they'll never be forming a uniform electric field. So whatever diagram we have seen, this is the only way a uniform electric field looks like. The lines of force will be parallel straight lines which are equally spaced. So this is another very important property of the electric lines of force. Now consider another very simple property of line of force. Now wherever electric field is present, there definitely E vector will be having some value. E vector will be having some value. Supposing electric field is absent, 0 at certain regions, electric field vector can be 0. E value can be 0. When is this possible? When there is no electric field at all. Such points where the electric field is 0. So for example, a simple example of this is like this. A very simple example. So this is the 6th point. So you take a positive charge and another positive charge. So between these two positive charge, the field due to this positive charge and the field due to this positive charge, they can be equal and opposite. They can just cancel each other. The field due to this positive charge will be directed like this, away from this positive charge. Similarly, at the same point, the field due to the right positive charge will be again directed away from the second positive charge. That means it will be leftwards. So both these fields are opposite. So if they cancel, what happens? In this region, there won't be any field at all. In this particular region, small region, there won't be any field at all. So a small region exists here where field will be simply 0. Such a region is called as a neutral region or a neutral point. Exactly at a single point it will be possible. Only at a single point this will be possible between a pair of like charges or a pair of positive charges. But at beyond this point, exactly at a single point this will be possible where field is zero. But beyond this point, at all the other points, field will be existing. So at this particular region where the field is zero, it is not possible for line of force to exist through this particular point. So exactly through a neutral point, no line of force will be passing because there is no field at all. So practically speaking, not just at this point, even in the small space surrounding this region, lines of force don't exist. So lines of force will never be existing. They will not be present at neutral points. So this is another very, very practically useful point related to the electric lines of force. So all these are various very simple properties of the electric lines of force.